So today we are going to learn all about scientific notation, which is a shorthand way of writing numbers that are either very large or very small. Anybody learn how to do scientific notation before? Good. Ideally, you picked up on this in like middle school and stuff. So I'm refreshing you and seeing if your head is still working and all those kind of good things. So say we have this number and this number. That first number represents your attention span. And the bottom number is my IQ. So we sometimes have numbers that are really annoying like this. And what is annoying about these numbers? There's lots of zeros. And so whether you have zeros at the beginning or zeros at the end, it's a pain if I have to write down this number. And if I made you write down this number, I was nice to you and I already have that written down for you. But if you had to write that number, it would be, did I count the right, you know, and it's kind of hard to write this down and get it done accurately. So we have scientific notation that helps us deal with numbers that look like this. When we do scientific notation, whether you realize it or not, you have done 4 steps. The first step says we're going to move the decimal to the right of the first non-zero number. So the first non-zero number at the top is going to be the 3, and to the right of the 3 would be right there. So you would move the decimal to that point. In the bottom number, what's my first non-zero number? You have some people that want to say 7 because they want to go by the zeros first, but no, in here in America we go from left to right when we look at numbers. So the first number we see is the 1, so to the right of the 1, we're going to move the decimal to there. So the second step is we count how many times did we move the decimal. So how many times am I going to move the decimal up here?
16.
Now what did you notice I did with my numbers here? I grouped them in groups of 3 because that's the way we think about numbers, right? So we've got that made. Lots of people like to put in commas. I don't like to put in commas. I like to put in spaces. So hopefully that won't freak you out, but I don't like commas because some people in other countries have found out that their commas are decimals, and that freaks them out. And why are there so many decimals in my number? And it also, if you photocopy things badly, then the commas and the decimals all start to look alike, and so I think spacing is easier. So yeah, here I can count this, and I go 3, 6, 9, 12, 15, 16. This one I'm going to go 3, 6, 9, 12, 13, 14. So we count how many times it moves. Second thing we're doing now, or the third thing, we're going to write out the significant numbers followed by times 10 to the n, where n is that number we just counted. After we do that, if our original number is less than 1, we're going to make the exponent negative. So this first number we're going to write down 3.21, and then we're going to write times 10 to the what? 16, but again, since this was a tiny number to begin with, that's going to be negative. Negative implies it's a tiny number. On the other one, we're going to write 1.87, and we're going to write 10 to the what?
14.
We counted 14, and this one stays positive because that's a big number. That's all you do. Those are our nice little steps. So, again, you move the decimal, and you write it down, and you put in a negative where there's negative. Now, you don't have to write times 10. You can also write an E. Guess what E stands for? Exponent. But so it's yeah, and the way that your calculator will represent it is usually like this. So if you prefer to write it like this, then you can write it this way. I tend to write it this way. Why? It's shorter. E is easier to write than times 10 is. Tough stuff, right? So, yeah, you should be smart enough to figure out, hey, these are talking about the same thing. So, that's all we got there. Any questions on scientific notation? Groovy. I will teach you a modification of this in just a few minutes. But we'd like to move on to standards. A standard is a system that has meaning to a group of people. What does this mean?
It's universal.
At least a group of people, it's universal to them. They understand that it has meaning. But what's an example of a standard? numbers. What? Numbers are kind of standard.
Colors.
Okay.
Prefixes.
I used to call up my grandma all the time. I don't call her up anymore because she's dead. It'd be kind of weird that way. But I used to talk to my grandma all the time, and I would call her up, and she liked to do gardening. And whenever she was out in the garden, then she would talk about the weather when she was out there. And so I'd call her up, and she'd say, "Yeah, I was out gardening today, and it got really hot." And I'd say, "Really, Grandma? How hot did it get?" "Got up to 87 today." Does Grandma live in Laredo? No, clearly she does not, because no one in Laredo would ever think 87 is hot, right? Okay, I take exception to that. If today got up to 87, would we think it was hot? Actually, we would. If it got up to 87 right now, you would start sweating and think, "Oh, it's really hot." But in our typical 105 summers, you look at an 87 day and say, "Oh, it's glorious. No one could ever sweat in this." So, anyway, when Grandma was throwing out that word hot, does hot have the same meaning to everybody?
No.
No. In this room right now, I think it's a little bit cold. There's probably somebody in here who thinks it's freezing. There's somebody in here who thinks it's glorious, and there's somebody who's like, "Turn on the fan." There's always a bunch of people like that. No matter where I am, people are complaining that it's either too hot or too cold. So hot and cold aren't really standardized. But when I threw out that number 87, did that have meaning to you?
Yes.
I didn't even have to stick a unit behind it, because you are used to, when we talk about hot or cold, if I throw out a number, we're talking about what? Degrees Fahrenheit. And that's what we're talking about there. If we were in centigrade and she said it was 87, you'd be worried about my grandma. Yeah. So that's a standard. Now, originally our standards were kind of strange. Standards were based on body parts, which was really nice, because no matter where you went, your instruments were there with you. And so that was really common. So we had body parts that were like cubits and spans and hands and feet and yards. What's a cubit? It's part of your body, man. You should know it. The cubit is the distance from here to here. How many people have a cubit? Lies, you have 2 of them. What's a span? Span is when you pretend you're a surfer dude. And it's from the tip of here to the tip of here, so that's a span. A hand is the distance across your hand. So if you measure up something like this, you're measuring in hands. Does anybody know what we still use measuring in hands for? No equestrians in the room. People who are into horses, they measure the height of their horses in hands. You start up their front leg, and when you get to the top of their shoulder, "My horse is 16 hands, he's huge." Foot. How many people have heard of a foot before?
Really?
What's
That's
that? What is a foot?
Latin word.
And people will say a foot is 12 inches. Yes, a foot is 12 inches, but that's a standardized foot. But originally a foot was that thing at the bottom of your leg that you walk on. And you would measure with those, because you can like go heel to toe, heel to toe, heel to toe. And you can measure something off like this, and that would be measuring off in feet. Now that has become standardized to being 12 inches, which is the size of the square on the floor. So if you compare your foot to the square on the floor, my foot's pretty standard. Some of you have substandard feet. You little people. You're gonna go home today crying. It's Boston said I had substandard feet.
I went over.
And what is a yard?
3 feet.
I know you're dying to say 3 feet, but in your body, what is a yard?
You're Hawaii.
Yeah, originally they measured yards in fabric, and if you went to a fabric store and they measured off a yard, they would just grab the bolt of cloth and rip it out to here and say 1, 2, 3. So the distance from here to here is, if you're a normal sized person. So, yeah, if I a yard comes to here, so that's pretty normal for me. I'm fairly standard. So that's a yard, and a yard became standardized to be 3 feet, but yeah, that's how we originally had yards. Now, it's great when you measure in body parts, because if you're doing the measuring and you're doing the cutting and you're doing the assembling, it doesn't matter. I can do this. This is going to work out great. I need to build a board that's going to fit across this table. So I measure this and I say this is 1 cubit, that's 2 cubits, that's 3 cubits, and a span, and 3 fingers of a hand. Okay, so if I go home and I measure out 3 cubits of a span and 3 fingers of a hand, and I cut this board off and I bring it here tomorrow, is this board going to fit nicely here?
Yes.
Yeah, because the same thing that measured it here is going to measure it there. No problem if I'm doing all the work. But if I send you guys all home, and you have to take that same measurement, and you have to cut it, whose board is going to fit?
Yours.
Probably nobody but mine, right? So we have a problem with using our body parts once we become a more mechanized society. When we start to say, okay, you're going to build one piece, and you're going to build one piece, and you're going to build one piece, and we want all of our pieces to fit together, if we're going to do this, we need a standard. We need something that everybody can agree on. So in the English standard units, these are ones that came out of England, and every country has their own unique set of weird units, and all of these came out based on the way that we just live life. So in length, we had to learn inches and feet and yards and rods and furlongs and miles, and these are all units of length. For volume, we had ounces and teaspoons and tablespoons and cups and pints and quarts and half gallons and gallons and pecks and bushels. These are all units of volume. That's the way it worked out in the English system. This system is stupid. You should have learned about this in history class, and that's it. And you should have said, that's funny, it's so weird. And you shouldn't have known any of this. Now, there's probably some of those that you still don't know because you don't deal in those very often. But in reality, this is comfortable to you because you're familiar with it. But it's horrible. It's a very bad system. For instance, how many of these are in this?
12.
How many of these are in this?
36.
How many of these are in that?
3.
Okay, how many of these are in that?
5,200 something.
That's 5,280 is just the easiest number to add, subtract, multiply, divide with, right? Who in the world came up with that number? Who came up with 12 and 3? I love to multiply by 3 and 12 and 36 all the time. We get to hear how many ounces are in a teaspoon. How many teaspoons are in a tablespoon?
3.
How many ounces are in a cup? 8. This is your system. Man, this is horrible. So anyway, here we got 3, here we got 8. If we go from ounces to gallons,
Oh,
some big number, man. How many cups in a gallon? You guys are like, okay, there's 2 in here, and then 4 in here, and there. Okay, you can see how it's weird. It's like, okay, if I chop this in half, I got a new unit. I chop that in half, I get a new unit. I chop that in half, I get a new unit. That's a lot of it. There's 3 pecks in a bushel. And you're very confused because you thought a peck was a quick kiss. So it's a very strange system. But it's familiar. And so we say, oh, it's great. I love this system because I'm used to it. It's bad. It's very, very bad because it really is confusing. So there's a better one. What happened was a group of people decided, you know what? It would be better if instead of me trying to talk to somebody in France and they have a completely new system of units and I have to learn theirs, how about if we all speak the same language? We all have the same units that we can talk about. And that makes international trade much easier. And so we came up with the metric system. Actually, it was invented by a group of scientists who wanted to discuss things with each other more logically. And so they came up with this system of units, and they said, hey, this is going to be great. We also call this the metric system. But what was cool about it was developed to be a worldwide standard. So everybody in the world understands this. And everybody in the world uses this on a daily basis except... Now you have to understand something about this. This has to do with politics. You see, Congress actually passed a law that said we would be completely converted over to the metric system by 1978.
Oh, Lord.
1978. None of you guys ever should have heard of any of those words that we had on the previous page other than in history class or on Trivial Pursuit or something. But you have got stuck with them because what happened was Congress passed this law because, yes, we're going to do it, everybody else is going to do it, the other nations just said we're going to force you to do it, but we live in supposedly a democracy, we're a representative government, but since we live in a semi-democracy, what happens is we have these leaders who get elected and they feel pressure from people. And so instead of being smart, which I know smart politics, anyway, it's kind of difficult. Every once in a while they come up with a really good idea and people are resistant to it because people are resistant to change. They're like, well, I'm used to this stuff. And what happened was we were like, oh, we're going to go metric. And I was in like 4th grade or something. And it's like, we're going to go metric. And we were learning all about the metric system. And then what happened was there was a new election cycle. And everybody was like, if you force that metric system on me, we're going to kick you out of office. And so everybody changed their mind and bailed. Every other country said, you know what, this is going to be better for our nation. I know it's going to be painful for a couple of years, but you're going to get through it. And they forced their nations into it. And we still haven't. Since way before you were born. It's really kind of sad. Because what's cool about the metric system is it's really easy to use because there's only one unit per variable and there's only one set of prefixes that work with everything. So, in the English system, how many units of length did we have right there?
6.
We had 6. So you had to learn 6 units and you had to learn all the conversion factors in between all of those, which were convenient numbers like 5,280. In the metric system, you have 1 unit. If it says meter, it's length. Any form of meter is length. For volume, it's going to be liter. For mass, it's going to be gram. For time, it's going to be seconds. For force, it's going to be newtons. For power, it's going to be watts. For energy, it's going to be joules. That's all there is. Volume, how many volume units did we have in the English system there?
2.
We only had 2. We had teaspoons and tablespoons and cups and pints and quarts and gallons and sacks and bushels. We had a bajillion of them. And in the metric system, we have 1. If it says liter, it's volume. How many people think right off the bat, this one sounds easier? Okay, now here's the cool part. There's prefixes to make them bigger or smaller. And if I learn this one set of prefix, it works not only for these units, but any other thing I ever learn. Already have learned. And so if we want to make them bigger, we have these. These are in a little chart on your notes. So we have petatera, giga, mega, kilo, and the base, and these make us bigger. If we want to make ourselves smaller, then we have centi, milli, micro, nano, pico, and femto to make us smaller. Now, what would be a logical letter to use to make it bigger for peta?
P.
What kind of P? A big P, because I'm trying to make it bigger. Then tera would be big T, and giga would be big G, and mega would be big M, and kilo would be, you would think it would be big K, right? But again, the one that gets used the most by people is kilo, because that's the closest one to the base unit there. And so kilo, because it gets used so often by common people who haven't been taught by me, they don't know that this should be a capital K, and they just made it a little k, and you can't smack 11 billion people and say, sorry, you gotta change it because Paulson says so. So, sadly, that should be a big K. Over here, all of these should be lowercase, so centi is going to be little c. Thank you. Millie's gotta be little m. Micah's gotta be.
MC.
We have a problem here. What's the problem?
There's
Too many m's. Over here we got a big and here we got a little and now I need another little and I'm in trouble. So now what do?
add another letter.
No, we don't want to add another letter because we always just want to have one letter for a prefix and one letter for a base.
Change it.
Z.
We could change it to something different, but sorry, it doesn't work that way. If we run out of English letters, the language we tend to switch to is a language that doesn't use, we couldn't switch to Spanish because it would still be and still look the same way and that wouldn't help us. So we switch to something that has different letters. So we switch to Greek. So we're going to go to the Greek letter, big or small?
Small.
Small. So the small Greek letter mu looks like that. So if that looks strange to you, it's because you don't speak Greek. If you speak Greek, you're like, duh, that's mu. Okay, so switching back to English, nano should be
Small.
what kind of n?
Small.
Little n and pico should be? Little p and femto should be? Little f. Now, what do these mean? Well, they all have an exponent to them. And if you look at the exponents to them, you start noticing, ideally, patterns. That's one of the signs of upper level thinking, is the ability to notice patterns. And you guys, of course, can think. So, what pattern do you notice? Hey, they jump by threes. And those of you who are observant start thinking, wait a minute.
They go that by one. Oh, wait. The centimeter.
One of these things is not like the others. Did you guys play Sesame Street? Did anybody watch Sesame Street? They had a little game that was like, one of these things is not like the others. One of these things doesn't belong. Which one doesn't belong here?
Centimeter.
Yeah, centi. That's why there's a little star next to it. This is our freak. It does not match our pattern. So if we just have one letter, then we're in our base unit. So if we just have one letter, then we're just like So if is by itself, I have people that get confused. And they say, does that stand for milli? No, milli is always the first letter. If it's one letter all by itself, it's a base unit, so it has to be meters here. But if I stick a letter in front of it, it changes what it is. And so I can stick a big P in front of it, or I can stick a little p in front of it. Is there a difference? Slightly. Big P is 10 to the 15, so that's a 1 with 15. 3, 6, 9, 12, 15. That's a lot of meters. But if we have a little p, then we're at negative 12. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So just a small difference between these two numbers. Okay, there's a huge difference. So you got to be really careful when you write things down, especially in your p's and your m's and things that show up on both sides. So that would make a big difference. But the reason that we jump by threes here is because, is this not how we think of numbers? I don't know, maybe you guys don't. I'll put in commas for those of you who love commas. Okay, so if we have a number that looks like this, these numbers we think of as our normal numbers, and then these are our thousands, and these are, and these are, and then after that is, and after that is, I always like to go to that one because people just start making up stuff after that. Gajillion, man. Okay, so this is what we did. These are our normal numbers, and this is thousand, million, billion, trillion, quadrillion, and so on up the line. So it goes like that. That's the way we think about numbers, right? So what's cool is if you learn these prefixes, you can do all kinds of little shortcuts. Like, what if I just want to get rid of these 6 zeros? What stands for 6 zeros? Okay, so if this was liters, then I could just write 1, 2, 3, 9. And that's the same thing, right?
Yeah.
And you're like, dude, that totally is. M stands for 6. And
Sorry.
so this is called engineering notation. And nerds like to use it. So, like me. So that's a good thing. Now, there's not a whole lot in this class that I require you to just straight up memorize. But you know what? What's my name? How do you know that?
I don't know.
Were you born with that knowledge? At some point, you had to stick it in your head and get it there. I'm going to have to stick 105 names to associate with faces. And the only way I can do that is by straight up memorizing. I'm going to have to memorize 105 faces. You guys are going to have to memorize this letter goes with that number. Okay? So it's going to be helpful to you. Make little flashcards or something, have it made. But you should know that peta is 15, tera 12, gig is 9. You should know that. Okay? So I do want you to memorize that. It's going to help you later in life. So, yeah. Moving on. Here's a number. What if we want to change it to something else? Well, that something else is cool in the metric system. It's very easy if I know my prefixes. So we like it a whole lot more in the metric system. Now, again, if I wanted to change this into a more reasonable number, what if I just wanted 187 and I wanted to stick in a prefix here?
Big G.
Big G stands for 9 zeros. So I can get rid of the 9 zeros and replace it with a big G. Is that a whole lot shorter to write? Is that even easier than scientific notation?
Yes.
Yeah. That's why engineers like it, because it's easier than nerds. You like that? Anyway, so that's good. But if we're going to switch in the metric system, we got it made. Now, what if I told you we have 1.43 miles and I want to know how many inches that is? And you have to do it in your head. How long would we be here?
Forever.
A long, long time, because I'm going to have to multiply 1.43 times 5,280, and then I'm going to have to multiply by 12. Might be able to pull off the 12, but pulling out the 5,280 in my head is going to hurt. Who came up with that number? On the other hand, if we are using the metric system, what is similar to a mile in the metric system? A kilometer. What is similar to an inch in the metric system? Centi. By the way, I didn't talk about this when we were on the other page when we were talking about the things. We said centi is a freak, but why is centi there at all? What happens is when people were making the metric system, they made the jumps that jump by threes because that's the way we think of numbers. But then the people who made the metric system made one mistake. They thought that in that common area, people would like extra bonus units in the middle there. And so they invented deci and deca and hecca and hiccup and these weird ones that nobody on Earth uses. And everybody in practical reality said, that's stupid, we're not going to do that. And so they died away everywhere except in American classes where they're teaching you about the metric system, because sadly you have some teachers that don't really know the metric system and they just read this in the book, and the only units they ever teach you are the ones that you will never encounter in real life. So I apologize for those teachers. But I'm not going to do that to you. I'm teaching you these prefixes and you will run into these prefixes in real life. But what you're never going to run into is centi attaching itself to anything other than meters. So there is no centiliter, there is no centigram, there is no centisecond, there is only a centimeter. And centimeters hung out because in English we like an inch, and a millimeter was just too dang small. So we liked the centimeter. It was like a midget inch. We could attach ourselves to it. We liked it. So centimeter stuck around, and because everybody's influenced by America, centimeter is used worldwide also. But that's the only thing. If you go and ask for a centigram of something, people will look at you strange. Like, what are you talking about? Okay, so back to our regularly scheduled programming. If we are switching from kilometers to centimeters, this is really, really easy. All I have to know is kilo stands for 3. And centi stands for Negative 2. So if I'm going from 3 to negative 2, did that get bigger or did I get bigger or smaller?
Smaller.
That got smaller. So this number needs to get
Smaller.
bigger. Okay, now this freaks some of you out because you're not thinking. Okay, what if I had $1.43 and I wanted to switch to cents? What is bigger, dollars or cents? Dollars is a bigger unit. So if I'm switching to cents, I'm going to need 143 of these to equal one of those, right? When my unit got smaller, the number had to get bigger for them to be equal. Does this make sense?
Yes.
So if I switch to a smaller unit, I'm going to have more of them to be equal. So how much smaller did I get here? 5. There's always somebody who wants to scream out 1, but they forgot the number line thing, right? So I go from 3 to 0 and then 2 more. That's a total of 5 smaller. So this has to get 5 bigger. To get 5 bigger, I don't add 5. I move the decimal to make it 5 bigger. So if I make it bigger, 1, 2, and how many zeros do I need? Hey. That was just bizarre.
Can't see what you do. Sorry. There we go.
That was really strange. Okay, anyway, so we'd end up with this. I move it 5 places. It started off right here, and it just moved 1, 2, 3, 4, 5. Now, did I need a calculator for that?
No.
All I needed to know was kilo is 3 and centi is -2, and I can count. If you can handle that, you can handle this. How many people learned a different way of converting in chemistry class? They taught you. They taught you to do.
Oh,
Oh, yeah.
Oh, God.
Okay, how many people think my way is easier? Because it is. Now, this has a lot of value in chemistry class because they were going to teach you stoichiometry too.
Oh,
And so they taught it to you this way because it makes more sense, but my way is always easier. Just remember that. Just keep saying to yourself, Paulson's way is the right way. Yeah. Moving on. What if I had picoseconds and I wanted to switch to milliseconds?
It would have to get.
I'd have to know pico is
Pico.
-12 and milli is -3. Now, if I'm going from -12 to -3, did I get bigger or smaller? I got bigger. And some of you are freaking out. No way, man. 3 is smaller than 12. Okay, but it's negative. So again, negative, we're down here. So if we're -12 up to 3, if you look on your chart, it makes more sense. So if we start at -12 and move up, they're getting bigger. How much bigger did it get? 9 bigger from 12. 12 minus 3 is 9. So that got 9 bigger. So that means our number has to get 9 decimal places smaller. So if I make it 9 smaller, it's going to go 3, 6, 9 right there. Super duper simple. We like this. Don't even need a calculator. Okay, we're going to switch to something that is completely different. What is this talking about? Terabytes. And you're saying terabytes? That wasn't on our list of units. You're right, but does it work with these prefixes?
Yes.
Every time I use a new thing, it still means the same thing. So tera still means 12, and mega still means 6. So how much difference is there between 12 and 6? 6. So how much bigger did this get? 6 bigger. If I have a 1.5 terabyte hard drive, that's really got 1.5 billion megabytes in it. That's crazy. That's a lot. Yeah. It's funny. This happens where we have computers, and some of you are not into computers at all, but some of you are. But yeah, the very first computer I ever had that had a hard drive in it had a 40 megabyte hard drive. My friends were so jealous. They were like, Paulson, you are never gonna fill a 40 megabyte hard drive. And you guys laugh at that. But realistically, now our hard drives are measured in terabytes, but by the time your children are in class, they're gonna be laughing at you. Seriously? It only held a terabyte? Like my iPod holds a petabyte already. Got every movie ever made right there. Okay, anyway, what I would like you to do for homework is problems A, which means you need to move to your homework sheet. And if you look at your homework sheet, it says Unit 1 problems at the top. Guess what that is? It's your homework sheet. So if that's your homework sheet, then from now until Unit 1 is over, that's where you're going to find your assignments. Have I talked about lugging along a big heavy book? No. Apparently you can get a book at the book room if books are your thing. But most of you stick those underneath your desk or lose it or something, and I'm not going to ever require you to actually do that. If you want one, they're there. I use them to balance out the table legs and things. I haven't looked inside of them, but rumor has it they're good. So if you want one, you can get it. You certainly do not need one. Anyway, your worksheet there, problems A starts where it says A. And it's going to stop when you hit B. So you're not going to do that whole sheet. That whole sheet is what we're going to do over the course of a week. Right now we're just going to do problems A. Now if you look at problems A, there's actually 3 sections. So the first section says, convert this into its base unit. So the first one said what, 230 nanometers?
Yes.
Yeah, I can write. Nanometers. Okay, if I'm doing a base unit, then I'm gonna basically, if the base unit is saying the prefix go in away. So that means I'm just going to straight meters. Well, nano was what? -9, and if I've got nothing here, then I have nothing over the top. So base units, you got it made, I'm always going to go to 0. So if I'm going from -9 to 0, that got 9 bigger. So this number needs to get 9 smaller. So this is going to be 3, 6, 9. How many zeros are going to be at the beginning?
6.
So it's just going to be 1, 2, 3, 4, 5, 6, 2, 3. That's going to be how you do the first one. Now the second part. What number is that? So if we jump down to 11, that's the second part. Now in the second part, we're not going to the base unit. We're going to whatever I asked you to go into. And in this case, we got 0.000238. 0.000238 megaliters.
Do we solve it in the same
And we're switching to milliliters. Okay, you know, you want to do this on another sheet of paper because you're gonna mess yourself up. But anyway, mega is 6 and so again, this is going to be 9 smaller, so this is going to get 9 bigger. So 3, 6, 9. How many zeros are going to be at the end?
3.
2, 3, 8. Okay, the third part of your assignment. There's a line that everybody likes to skip. Right above where it says B, there's one more instruction line there. And it says change all the numbers typed above into scientific notation. So I'm not asking you to change your answers. I'm saying the ones that are actually physically typed, which would be these numbers. So I want to change that to 2.30 exponent 2. This would be 2.38 exponent -4. Right? Yeah. Okay, is that the only thing I want you to do for homework? No! If you look on the back of your note sheet, There's this convenient little touch list. Now, where it says second block, you don't have to do those last ones because that was this first semester. So you got me. But those 4 little things, I want you to do problems A. I want you to bring back your signed free AP compact form. I want your parent contact form, just the bottom part, and I want you to sign your parents up for the phone texting. Any questions?
Yes, sir.
Yeah. Well, that's it then. Have fun. See you tomorrow. Or something.
Like,